The information we can obtain from a carbon-13 spectrum is limited. From the number of signals, we can determine how many sets of equivalent carbons are present in the molecule. From the chemical shifts, we can establish what types of carbons give rise to the signals. This spectrum shows 5 signals. The triplet at 77 parts per million is caused by an NMR solvent, deuterochloroform. The signal at 0 parts per million belongs to the carbons of TMS, the internal standard. The sample gives 3 signals, indicating 3 sets of equivalent carbons. The first signal has a chemical shift of 171.4 parts per million, which is characteristic for the carbonyl carbon of a carboxylic acid, ester, or amide. The second signal has a chemical shift of 51.5 parts per million. The third signal has a chemical shift of 20.6 parts per million. They both fall into the aliphatic region. This is the carbon-13 spectrum of methyl acetate. Signal 1 comes from the carbonyl carbon of the ester. Signal 2 comes from the methyl group adjacent to the strongly electron-withdrawing oxygen. Signal 3 comes from the methyl group adjacent to the weakly electron-withdrawing carbonyl group. The sample leads to 5 signals in this spectrum, indicating 5 sets of equivalent carbons. Signals 1 through 4 have chemical shifts between 137.7 and 126 parts per million, which fall into the region for aromatic, vanillic, or nitrile carbons. Signal 5 has a chemical shift of 21.3 parts per million, which falls into the aliphatic region. This is the carbon-13 spectrum of M-xylene. Signals 1 through 4 belong to the aromatic carbons. The smallest signal is caused by the carbons labeled 2, which do not have attached hydrogens and receive little NOE enhancement. Without a correlation table, precise peak assignment for the remaining 3 peaks is difficult, and thus not required here. Signal 5 comes from the methyl carbons.